Okay, thank you everybody for being here this morning. Again, Marcos sends his apologies. He's actually bedridden with a horrible case of the flu. And for those of you expecting Marcos, yes, he is taller, he is more charming, and he has more data than I do right now. We're in the middle of a collaboration that we think is going to be very productive. And I'll talk to you about some of that data, also add some data from our GCHRT platform, all around a petroleomics or petroleum characterization paradigm. And then upon my completion, Yuri Carrillo will talk about a software package that is part of this collaborative effort and part of our effort to provide characterization tools for petroleum analysis. Why the collaboration with the Thompson lab? Well, and that's Marcos's lab. You know, the lush green forests of Brazil, the banks of Lake Michigan. I mean, the obvious tie is petroleum and mass spectrometry, right? Am I missing something? Anyway, outline of the talk for the API section, so the CITIUS portion of the discussion, will be why are we looking at petroleum, what is it characterized? Some of you already know that, but it'll give us give you our perspective. TOF versus FT. Some of the capabilities of the zigzag TOF, as Marcos refers to it. I won't get into that too much because Nick already provided that introduction. And then actually some comparative data, acquired side by side, same samples, trying to demonstrate the same information content from those. So why characterize? Well, there's a lot of diversity in petroleum reserves, and that's important to oil companies. New sources, such as the oil sands, the age of the reserves, and the heteroatomic distribution amongst those. The characterization can ultimately affect yields, processability, and mobility, all of which ultimately cost money. And that's important to all businesses, petroleum included. Analytical techniques that have been used historically are NMR and GC with FID for the quantitative analysis and MS and elemental selective detections for the characteristic aspects. Also physical physical techniques. And then of recent, relatively recent, API-MS with FTMS really leading the way. It has been king for decades. And I call resolving power greater than 100,000. It's far greater than 100,000. And if you go visit Alan Marshall's lab, you can see really big numbers and a really big instrument. The challenges that have driven the variety of these techniques and the approaches are the similarity. Carbon, hydrogen, nitrogen, oxygen, sulfur. That's pretty much it. But also the complexity. The way those are pieced together create a myriad of products that require a high level resolution and very high accuracies to facilitate their characterization, with a discrete number of analytes being in excess of tens of thousands. The distillation of information is ultimately what's important, and that's where the software comes in. M over Z's don't matter, I don't think, to petroleum engineers. If you give them an M over Z, they're probably just going to look at you funny. So what's important? Why a mass spectrometer? Speed and simplicity. Okay? It takes just a couple minutes to run the experiment. That's actually the easy part. The hard part is the dissemination of information. The performance needs, you need to have effective resolving power, enough to get the information out. You need stable mass accuracy, and you need general system stability. If you have drift in resolving power or in mass accuracy, you will not have a successful experiment. Ultimately, though, as I said, it's information content that's important. So why mess with FTMS if it's been around for so long and has been successful? Well, it's expensive, approaching $1 million, and it's needy. You have to feed it. You have to feed it liquid nitrogen, liquid helium, and then it occupies a lot of space. This is our FFP, or high resolution folded flight path technology. I won't go through the descriptions here because Nick covered that quite well, but I will point out a couple of couple of key attributes in its performance, and that's around resolving power and how it performs versus other opportunities. So here is in the green, a resolving power profile or resolution profile for the HRT versus a conventional TOF. We have a flatter profile because of our long flight path, more forgiving, and at lower M/Z that provides a higher resolving power than traditional TOFs. Here is a comparison versus FT instruments. Those have the well-characterized dip in resolving power as a function of M/Z. Again, the HRT, we have a relatively flat profile, so we provide some advantages and opportunities at higher M/Zs versus an FT. And the experiments that we'll talk about today are strictly in ultra-high resolution mode on the Sirius, which is about a ppm mass accuracy, and 100,000 or higher resolving power. For the sake of brevity, I'm going to skip this slide, just compares and contrasts. And I mentioned information content previously. So this is about spectral capacity. What can you get out of an experiment? So this is an FTMS in red, and this is how many fully resolved spectra can you get as a function of M/Z. You can see at your low M/Zs, you probably get some benefit here, but it makes up out here where the TOF provides more information. And then if you look at it in bins, you can actually see that between 250 and about 1,000, the TOF actually starts to provide more information content, which is really where the petroleum characterization is most efficient and most significant. So experiments, again, very simple experiment. In this case, it was a direct infusion or direct analysis, either with a syringe or a nanomate, interfaced to either Vasidius or to a 7.2 Tesla FTMS made by another company. And the data were processed using PetroOrg software. Brief depiction, and that's the one good thing about petroleum. There's rarely a scarcity of sample. When you get a 55-gallon drum as your sample submission, that's pretty good. So for spectral comparison, let's get to the data. Okay, that's really why you're here. This is an FTMS. This is an HR TOF at the bottom. Same sample, done very close to the same time, same preparation or similar preparation. Resolving power about 100,000 here, and FTMS 400,000, but at the lower mass range. There are differences in the distribution, but remember, there's very significant differences in the ion optics between these, and we have other data that's not included here that we can certainly share or discuss, where we can change this profile, or they can change their profile by changing ion optical parameters that cause biases in where the distribution of M/Zs are. So I'd ask you to not focus too much on this, but focus on the meat, which is the M/Zs, the measurement, the information content. So what I've got here is a zoom in of a 10th M/Z window from these two spectra to compare M/Zs and information content. If you don't see an M/Z, you're not going to get an identification clearly. And if you compare the two, FTMS at the top, HR TOF at the bottom, they're all but indistinguishable. From a performance perspective, mass accuracy stability here across the M/Z range, approximately less than 1 ppm, RMS 0.63 for the FTMS, and below the HR TOF, RMS mass error of 0.91 ppm. Top 600 spectral peaks included and identified, and the bottom 700 spectral peaks included and identified. And then, as I mentioned, the resolving power difference, and we'll leverage that throughout the content of this talk. Excuse me. Systems have to have stable resolving power, and they have to have stable mass accuracy. So this is a plot of resolving power here, mass accuracy here versus time. It looks very chattery with a little bit of noise to it, but if you look at the scale, it's actually quite tight in a relative perspective. With 100,000 here and 140,000 here, we're consistently in the 120,000 range on the HR TOF, And for mass accuracy, again, 1 ppm, consistently within plus or minus 1 ppm mass accuracy. So the general attributes are there to be able to have successful experimentation and to derive the type of information that you can get from an FTMS experiment. Real resolving power data. The top is a crude oil sample looking at the O2 class of compounds. You see a nice profile here, some scatter, because the measurement of the properties, whether it's mass accuracy or resolving power, are going to be intensity dependent. It's a statistical process. Here for standards, you see almost the same curve as you see here, which is very encouraging. Now let's get down to brass tacks. This is the most challenging measurement that a mass spectrometer will need to perform in a petroleum sample, and that's the C3SH4, I call it exchange, but it's not literal, where you have two formulas, same nominal mass, differing by only a few millidaltons. Theoretically, this requires in excess of 85,000 resolving power to achieve it. Can we do it on the FT, or can we do it on the HRT? Actually, we can. If we look at this pair here, this is a distribution of a crude oil sample. Look at this pair, and you can see by the inset, we can in fact detect and resolve those two species that differ by approximately 3 millidaltons. And that lets us do a very robust characterization. Additional critical resolving power, or critical pairs. Here's a difference that should be about 36 millidaltons. We measured at 30, it should be 36.4, we measured at 36 even. So we are spot on with our relative accuracy as well as our absolute accuracy. And then we can, of course, get information on homologous series, leveraging the accurate mass and the resolving power to create a lot of space. And this is a series of the C3SH4 exchanges. So we can't do it just once, we can do it across an entire mass range so that you can track that content across the entire product. Ultimately, the goal is to get information on what classes of compounds are available and what need to be modified for processing. Here we extract the O2 class and the N class from negative ion electrospray, so the naphthenic acids and the carbazoles, from 3 different samples. So we can see some level of discrimination between classes as well as different types of petroleum samples. We can also get information on double bond equivalence by processing with PetroOrg software, which again lets us see the distribution of compounds for processing purposes. And this can be put into different visualizations. Here a 3D plot or a heat map of sorts, which breaks down, again, the naphthenic acids into their different forms, indicating the rings and the complexity versus either carbon number or double bond equivalence. Again, direct comparison to the FTMS. Here, the HRT is in blue, FTMS in red. This is a negative ion electrospray looking at, again, the elemental distribution of those components with the different classes indicated at the bottom. The relative trends are very comparable between the two, with a peak at the O2 and lower levels of S and N. This is an N of 1, no statistics around this particular experiment. And then comparably, the double bond equivalence between the two systems, FTMS and HR-TOF, show very similar distributions. So the information content between these two for an N of 1 is relatively comparable, if not indistinguishable. Again, another comparison, different sample, positive ion, ESI, negative ESI, broad ranging distribution. This one much heavier in the N1 class for both, but comparable results from HRT and the FTMS. Visualization, this is, I think, a very pleasing and easy to interpret plot. Okay, you can see where there's intensity and you can see where there's not, but comparison of the FTMS and the HRT, resolving power of 100,000 on the HRT versus 400,000 on the FT, very comparable distributions with outstanding qualitative results between the two here. Finally, can you differentiate? Okay, we had one example where we looked at the class distributions, and we've had two samples where we looked at elemental composition at a fundamental level, but can you really differentiate three different classes? So we have three samples here that we looked at by FTMS and HRT from very different sources that would be predicted to have dramatically different elemental compositions or heteroatomic compositions. These are provided here for positive ion electrospray and negative ion electrospray. As you can see very clearly, broad range of distributions, nitrogen content and naphthenic content, so the carbozols and the naphthenic acids predominantly. And looking at them in a more visual and elaborate layout, you can see very discrete differences in this case, the NO2, where each has a very unique profile. And then here for the naphthenics, again, as a plot of double bond equivalence, how does the distribution relate? So the TOF has a very clear capability of differentiating and breaking out the contributions in a manner very similar to what's been achieved with FTMS in the past. And then in this case over here, this is just two different diesel samples profiled in the same way using negative ion electrospray, showing the differences in distributions. So with the CIDIUS and the high resolution, we've been able to demonstrate that we have enough effective resolving power to answer the critical questions. The SH4-C3 exchange being the critical pair. We have mass accuracy and system stability across the experiment to get reliable results. And we can extract information with the aid of things like PetroOrg software to get the information content to be able to make decisions on petroleum samples, how to process them, and where they are critically different. And then finally, what are the implications? Well, the HR-TOF provides an effective, cost-effective alternative to FTMS, lower care and feeding, and it provides HRMS to the masses of sorts. So now I'm going to transition to petroleum analysis using the GC high-resolution platform. Give some brief examples of its capabilities, where we've applied that as well. For crude oil classification and some experimentation. What are the challenges? So heteroatomic compounds, and I got to recognize Dave Alonso for this data. Dave's in the back of the room, so if you've got questions, feel free, please. Sorry to put you on the spot, Dave. What are the challenges? Well, just like it was with the CIDIUS, it's heteroatomic species. Nitrogen content, sulfur content, oxygen content. These all create problems for catalysis and processing. And so what's that translate to for the mass spec instruments and the platforms available? You need to have broadband resolution. You need to be able to resolve things at low M/Z and high. You need high resolving power, and you need to be able to resolve discrete compounds and leverage all of this for isotopic information. Practical choice, we think, is clearly high performance TOF. It provides a comprehensive platform with high quality data, and it's easy to maintain, fast, with high resolving power. Let's start off by looking at some light crude samples. Here is the total ion chromatograms for 4 different crude oil samples, and we'll dig into a couple of these in a little more depth. Looking at the aromatic classes, here are some naphthalines and substituted naphthalines to give you an idea of what the resolving or the mass accuracy capabilities are. As you can see over here on the far, my left, your right side of the slide, mass accuracy is consistently below or right around 1 part per million, so you have very confident identifications. And that applies not just to the molecular ions, but also to the fragment ions. So this somewhat of an eye chart won't ask you to read. There won't be a test or anything on the mass accuracies, but the average mass accuracy is about 0.45 ppm across the entire mass range, which goes from small fragments to molecular ions. So a very robust platform with a lot of capability. Extending this again to additional polyaromatics, mass accuracies again to the far right, really emphasizing that because it's important for identification. Average of 0.5 parts per million for the mass accuracy for these aromatic compounds. And then finally, there's always other things in there that you don't expect, may not necessarily plan to characterize, but seeing them is always beneficial. It's usually, not always, but usually better to have more information. And these compounds, which were not necessarily targeted, but were found, were identified with the indicated mass accuracies, all shown here with this diversity of structure. And again, mass accuracies 0.91 for this class and suite of compounds. This is just a comparison. These are like crude oils, and then this is a biodiesel, a supplemented biodiesel. Very different profiles and very different challenges. One way to supplement those challenges or to help to address that challenge of complex deconvolution or complex samples, such as this, is through deconvolution. Okay? What's shown here, my right, is a raw mass spectrum. But by applying deconvolution, we're now able to leverage the accurate mass by getting a clean spectrum for a FAME, which is deconvoluted from this mess. So we can get a clean, well-characterized spectrum to get a robust identification, even out of that complex chromatographic display, as was shown here. Mass accuracy can also be leveraged in other ways. Hopanes and steranes are biomarkers in the petroleum world, often done by nominal mass, here 1,000 resolving power. If we kick this up to 2,500 or 25,000 resolving power on the Pegasus HRT, you can see that this goes to 2 very cleanly displayed and well-resolved species contributing to this signal. If we kick it up a little bit further to 50,000, you can see additional contributions at smaller levels. So the ability to get selective detection of biomarkers is achievable and potentially important in characterizing the petroleum. And this high resolution lets you be selective and more accurate in that evaluation. And then finally, hydrocarbons and petroleum compounds provide a lot of challenges. One of them is they are very fragile, especially hydrocarbons. Soft ionization is important because it gives you the molecular ion so that you can do robust and confident characterization as opposed to relying on the fragments. The options historically have been field ionization, which is a little bit of art. It's very strong and well used in the petroleum industry, and it does require a specialized source. Chemical ionization is the other option. It's flexible, broadly applicable. It too requires a special source or modified source. There are other options available, but those are probably the prominent forms. We've taken the chemical ionization approach, and I've got a couple of brief examples here. This is a jet fuel sample, simply looking at the N-alkanes, but in the absence of molecular ion, you're relying on retention indices and relative retentions. If you have a compound that produces comparable fragmentation, you'll have a problem resolving it and distinguishing it. However, by implementing chemical ionization, we get very robust pseudomolecular ions displayed here with very robust mass accuracies, again, less than 1 ppm mass accuracy. So we can confidently identify the alkanes, although everyone knows that they're there. The impact of chemical ionization is seen here, where you can have the prominent molecular ions, but you do still have fragmentation. So you can get characterization. You can understand branching. You can understand saturation, unsaturation, and substitution quite well, but still have the benefit of the molecular ion for accurate mass characterization. And then finally, again, with the jet fuel sample, chemical ionization versus EI. Okay, much more information content, accurate mass information, as opposed to dealing with an EI spectrum, which is sometimes indistinguishable from one another. Clearly, this is applicable to not just hydrocarbons, but also to substituted compounds. Here, sulfur and oxygen substituted compounds, where you get very clean molecular ions, and deconvolution can be applied to the accurate mass entities. And yet one more example, N plus H, N plus H. mass accuracies in the 1 part per million range. So conclusion, high resolution TOF interface to GC is applied to petroleum characterization and provides a robust mechanism for analyte ID. The resolution and resolving power, we think, facilitate the identification at 1 part per million mass accuracy. The identifications are strong and confident, especially coupled with chemical ionization, where you now have the ability to get molecular ions confidently and identify things in complex mixtures with the assistance of formula deconvolution. And when you put all of this together, have a very robust package of high resolution TOF for petroleum characterization. So with that, thank you for your attention.